Okay, so recording has started. So let me share the screen to solve the problem. Okay, so the first problem, if you see in the week 5, was related to the the PWM operation. Uh, so in that we have given that it is a 50 hertz fundamental frequency, and the carrier frequency is at 5000 hertz. So if you do a simpler mathematics, what we will get is we will have our frequency on the side bands of 5 kilohertz. The first harmonics, or you can say the first set of harmonics, will be on the side bands of 5 kilohertz, because let's say I mf plus j, we will plus minus j we will do. So I is, if we keep the odd one, so it is mf, which is nothing but comes out to be 5 kilohertz, and then uh, mf is nothing but fc by fm. So the number, the harmonic number will be near to, I mean, which corresponds to the 5 kilohertz. So we will have 5 kilohertz plus, so I we have kept it odd. Now when we keep the an even value for j, what we will get is 5000 plus 100 hertz we will get. So this one, first option is correct. Then 500 plus 100 hertz, so 5000 plus 100 hertz, we have 5000 plus 100 hertz, we have 5000 plus 200 hertz, and we have and so on. And then after that, when we keep the even term to be 2, I equal to 2, that means even I as even quantity, then your j will be odd quantity. So when we keep 2, I equal to 2, then it will be 10,000 kilohertz. Now when we keep 10,000 10,000 kilohertz, then so we have the harmonics near to 10,000 kilohertz signal. So 10,000 will be there. Then j, you have to, now you have to keep j as odd. So it will be 10,000 plus odd will be 50 hertz, and then you have so you have the harmonics at, in you will have harmonics at 5000 with plus j, which will be even. So you have 5000, you have 5000 plus 10 on one side, on another 5000 minus 100, and then you have 5000 plus 200 on one side, and so on this side you have 5000 minus 200, and so on. That will be the hertz. So this is there in the solution, that's first thing. Then on the side bands of even even harmonics of pitching frequency, so we will have 10,000. So that means j you have to keep odd, so there will not be any harmonics present at the 10,000. You will only have 10,000 minus 50, and on the other side 10,000 plus 50. Then comes the second odd one, plus 150, and here it is 10,000 minus 150, and then here 10,000 plus 250, and then here again 10,000 minus 250. So this was the value given in the solution, and this is also the value which is given in the solution. So that is what we have given the solution as A and B. This will not be there, this will also not be there. So that is what is the question. Yes, please go ahead, ask questions. Hello? Hello?
Hello.
Yes.
Yes, sir, if we do it by with that formula that you have given with that MF and I times of MF plus J, that will in with using that the MF value will be 100 hertz
Okay.
and and then all the options get satisfied
Uh,
using different I's and J's.
so MF is what you get FC by your
Okay.
FM. FC is your 5 kilohertz
Okay.
and it is 50 hertz. So that will be 100.
And-
Okay.
Yeah.
So first one will be I MF plus minus J. So I have kept first one as I equal to 1 into MF plus minus J. If I have to keep, what I will keep, so here I have put odd, so this will be even. So 2 4 like that. So
Yes.
now my thing will be, or a 0 will also be there. So what will be there? MF will be there, MF plus minus 2 will be there, MF plus minus 4 will be there. Okay. Now
Yes.
so you have at 100, you have at 102.
51 hertz.
Okay, 102. And this, when you do it with 50, so what you will get? 51. Okay,
Yes.
this is
Yes.
what I've written over here. And this is, if
Okay.
you put it is 104, you do 50, you will get this one only. You got
Okay.
my point?
Yes.
So if you keep this one as, again the second one, if you keep 2 times MF plus minus 135, you have to keep. So that will give you your 2 MF plus 1, 2 MF plus 3, and so on. So only these two options are there. You
Okay.
got
Okay.
you got my point?
Yes.
So that is what we were doing. Now in the second problem, okay, in the second problem, the question is of the form, so if you see this particular converter, it is not exactly the your flyback converter, only this part, let us say only this part. It is actually the what you can say tapped inductor based boost converter kind of configuration. So let us do that particular configuration and see how we can get the output. So if we just take this one here, we have modulus Vs which is coming over here. Then we have tapped inductor with a number n1 number of turns and n2 number of turns. Now and they are wounded on the same core. So if they are wounded on the same core, so in the DTS period, when your S1 switch is on, so you are now applying from let's say we define the term L1 and L2, and this L1 and L2, the voltage across them is plus minus, and the overall voltage across inductor is VL. So your VL1 is modulus Vs sin Vs t will become, because in this circuit if you take KVL you will get this value, while VL2 is the induced voltage which you will get it from whatever you are getting in the first inductor. So you will write N2 by N1 times Vs of t modulus Vs of t. So that indicate the overall voltage across this inductor is nothing but VL1 plus VL2, and that when you solve, what you will get is you will get modulus Vs plus N2 by N1 modulus Vs. This is the case, the voltage across this inductor during the DTS period. Then you see during 1 minus DTS period, in that period your S2 switch is on. If your S2 switch is on, then what happens? During that period, you are now applying from this place directly V0 voltage. So the overall voltage across inductor VL is nothing but modulus Vs of t minus V0. So this is the term which you will get during 1 minus d of Ts period. Now you do the same volt second balance in the entire line cycle. You do it and make it equal to 0, half line cycle, and make it equal to 0. We take the same approximation where we assume that the step change in the the average value of currents are very minimal, so we can, in that sense, we can approximate, and what we will get is this value, this entire term to be equal to 0, and that when you open up, finally you will get the value which is V naught minus modulus Vs divided by V naught plus N2 by N1 modulus Vs, and that is nothing but option number B. So you have to just do, if you are given any kind of power converter, you can just do the volt second balance around the inductor, and you can calculate the particular scenario, the voltage, the things around them. Now let us take the another terminologies, another question. So that is the reason why you have answer B, which is correct. Then comes the question number 3. In question number 3, this value is been given. So let us try to solve this question number 3. Again, in question number 3, directly you can use this formula, which is mv0 by 2 square minus vs peak square divided by 2 by fs is peak square. Your m value has been given, v0 value has been given, vs peak value has been given. Now what? Yes, any questions? Okay, I think no. Then you have your fs value is given. Only thing we have to calculate our is peak. So for calculating is peak, in a question it is given 10 kilowatt power level, and the also in question it is given that it is a lossless converter, so p in is equals to p naught, and it is given that line to line RMS voltage is 400 volt. So the phase RMS, or you can say phase voltage RMS, what you will get is nothing but 400 by root 3, and that's when you can calculate the phase current RMS, which is 10k divided by 3 into this thing. This will get this, and that will corresponds to our is peak to root 2, so that will be my is peak 20.41. This, when you put this value over here, finally you will get the L value, which is 4.933. That value you will get the correct value, and that is why the range is been given 4.9 to 5 millihenry. Then comes the question number 2. In question number 2, it is given that you have a standard half bridge converter, and it is having some supplying, let's say, it is not given anything, so let us take this one. It is VDC by 2, it is VDC by 2. Now it is given that the sampled value, so we have sampled that modulating signal which is coming from your controller, and that sample value is having a value nothing but equal to 2 volt. That means Vm is equals to 2 volt that they have given, and the carrier is going between plus 5 volt to minus 5 volt that they have given. So I mean, the question was, and they have also provided the frequency information. However, it is not needed. But anyway, they wanted to see. I mean, the question says that you have to calculate the average output voltage. So what we will do, we will, whatever the discussions we did in the class or in the lecture number 22, it's the same thing. So you just take, if let's say if you take this one here, it is minus 50 you are applying, here it is plus 50 you are applying. This is, let's say this is T on period when the top switch is on. Here they have given when the modulating wave is greater than the carrier wave, that means during this portion your top switch is on. That is why you are applying between A and O VDC by 2. Remaining of the time you will turn on this S2 such that the voltage across VAO is nothing but minus VDC by 2. So that you are getting plus VDC by 2 into T on period, then minus of this entire period is TC by 2, same as what we have taken in the lecture, minus T on, and this is again, this is TC by 2 over here, and this, when you solve, finally you will get 100 T on by TC by 2 minus 50. Now we have to calculate this T on by TC by 2. You can then define the slope of this line and then this line and equate them to the same value, and finally what you will get at half minus Vm by 2 Vc is nothing but equal to 1 minus T on by Tc by 2. And this Tc by 2, we have to calculate Tc by 2. So Vm, we know it is 2 volt. Vc is 5 volts, so it becomes 10. And 0.5 minus 0.2, it is 0.3. This side goes in, becomes 0.7. And that 0.7, if you put over here, what you will get is, you will get nothing but equal to 20 volt. So that's the answer which you will be getting at the output. So that's the question number 4. Then let us take the question number 5. Question number 5 is kind of the same question as that of question number 3. Same formula to be used. Same way you have to calculate the IS peak value, and that IS peak value you will get by putting your values in this way, and finally 10.2 ampere you will get IS peak value, and then from there M value you will get as 0.938. It's the same formula. What is the same procedure what we did in case of question number 3. Then question number 6. In question number 6, the problem is given, and it is given that uh, the peak of the fundamental component of output of half bridge is equal to 360 volt. They have provided that. So what it indicates, so the peak of fundamental is nothing but m VDC by 2 sin omega t, average value of half bridge, that we know VAO average, that for fundamental frequency, for fundamental frequency, it is m VDC by 2 sin omega t. So that is what we will get, which is 360 volt. And this 360 volt, you put it is m VDC by 2. VDC we know it is 800 volt is given. So m value will be nothing but 360 by 400, which is nothing but 0.9. And this 0.9 is there, you put it in this value, you will get value to be equal to 7.988 ampere. However, in the answer we have given the range 8.5 to 9, so we will increase that range such that this will accommodate within that range. So the correct answer is 7.988 ampere. That particular m equal to 0.9, when you put it over here, you will get this value. So that's the question number 6. Then let us take the question number 6 is done. Question number 7. Okay. Now in this case, in 3-phase AC/DC converter operating with unity power factor, what will be, what is the question number 6? No, there is nothing wrong answer. We will increase that range. That's what I am saying. We will increase this range from 7.5 to 9. So that correct answer will come into in between that. We will increase this range, so that if you have written the correct answer, it will come as a correct this one. So in question number 7, which of the following statement is true? Now in this thing, this is the unity power factor. In 3-phase AC/DC converter, it is given that it is operating at a unity power factor. Now this we know that in 3-phase AC/DC converter, when it is, we have derived in the class, as what we have seen in case of single phase. What we have in case of single phase, we have in case of single phase, on the output capacitance we have second line harmonic component. That means along with DC component, that was the dominant, plus DC component, that was the no, that we will increase the range, so you will get, the marks will be revised. Am I mean, Monica, is it okay? So second line harmonic component plus a DC component will be there. Okay, in that, in single phase case. So the dominant logic is nothing, dominant frequency which is present is second line harmonic, which is if you, let's say, if your line frequency is 50 hertz, so it is 100 hertz which will be there. In case of three phase, what we have is, we have a DC component, and there is no second line harmonic component, because when you do Vs sin omega t into Is Vs peak sin omega t into Is peak sin omega t plus Vs peak sin omega t minus 120 into Is peak sin omega t minus 120 plus Vs peak sin omega t minus 240 into Is peak sin omega t minus 240, it will all come down to be just the DC quantity. So we do not have any second line harmonic component. So there will not be any second line harmonic frequencies which are being present in the in your DC voltage, I mean voltage of the DC capacitor, output DC capacitor. However, there is line harmonic component which will be present, I mean the switching frequency harmonic component will be present, because in your, if you see in your I converter, in this I converter you have this switching harmonic component, because this switching harmonic component, why it is been present, because this I converter current is varying between, let's say, if A phase for some DTS period, this S1 switch is on, S1, S3, S5, S2, S4. In A phase, let's say for some DTS period, this S1 switch is on, so for that period I converter will be there, and then in 1 minus DTS period, if S2 switch is on, then there will not be any current in the I converter. So that is why what you will see is that this I converter will have the component which is which is having a switching harmonic current component will be there in case of I converter, and that switching harmonic component of current has to be filtered out by this capacitor C before going into the load, such that load will see only the average I naught current which is going into the load. So the capacitor C will have the switching harmonic component, and that is what we have done it in case of, I mean, while deriving the RMS component of current. So now we have the switching harmonic component of the current which is been present after the DC component. So beyond this we have switching harmonic component. See, that is what we have done. We have calculated the RMS in one switching cycle, and then we have calculated the RMS in the entire line cycle. However, if you see the RMS value of the current which is going through the capacitor, IC RMS, is independent of the switching frequency what we have. See, RMS component is what? It is a kind of a mean what we are taking, square of the means what we are taking. So that is independent of switching frequency. So the idea of telling that statement is, the capacitor which you are actually sizing for your three-phase AC/DC converter is independent of the switching frequency. Whatever switching frequency you will take, this C will not be dependent on that. So that is why I have introduced that, I have put that component, that RMS value of current, which is the mean value of component, is independent of the switching frequency. However, there is a switching harmonic current which will be going through the capacitor, because that has to be filtered out before it is going into the RL, because if you see the I converter current, it will look something like this. For some portion it is on 0, some portion it is on 0, some portion it is on 0, some portion on it is 0, some portion it is on which is 0, some portion on 0, some portion on 0, some portion on 0, some portion on goes to 0. So I mean, this is from single, from just A phase. Similarly, you can do it for B phase, C phase, and then you can add them together. So that is what what you will see over over there, that this kind of things will be coming into picture. So that is the reason why the switching harmonic component of current will be there, but there will not be any second line harmonic component. So switching harmonic component will go through the capacitor, and it will be responsible that will have you will see some kind of component corresponding to that. How much? However, those components are very small, that ripple will be very small. That's why you will see a pure DC component onto your capacitor voltage. So if you see this one in the question, um see current flowing through the capacitor, so that's why it does not have, this is first option is correct, and your it has switching frequency component. That is why A and D option is given correct. Then comes question number 8. In question number 8, again it is a straightforward question. In if a three-phase DC operating with UT power factor, then which of the following statement is true? Now uh, we have already discussed that in case if we derived in terms of phasors, so we can just define our phasors to be, this is Vs phasor, this is Is phasor, and this is your omega L Is phasor, this is your omega L Is phasor, and you have this is your V converter phasor, this is your V converter phasor. Okay, and what we understood is that we have already seen that whenever V converter is leading the Vs, so the power is flowing, backward power which is flowing from the V converter to Vs, or the to the source. In this case it is a forward, that means the power is flowing the from the Vs to V converter. Basically you can say whichever phasor is leading, the power will start from there and it goes to the other phase, source with phasor corresponds to the other source. So that is it goes to into the source correspond, goes to the second source for which the phasor is lagging the that other phasor. So that is what is all about. So that is why we have here in the question B option and C option which is present. The phasor obtained from converter must lag the source. It is correct. That means our source phasor is leading the. How do we control delta? Okay. So how do we control delta angle? So delta angle will automatically get controlled because we are changing our D and Q component. If you are doing the independent control of this particular converter, what that is what we have studied. So we change the D and Q component. The moment you change the D and Q component, your angle will change. So that is why you will be in a position to change that particular angle. You got my point? The Now in the fourth problem, a half-bridge voltage source converter operates or outputs a sine PWM signal with VDC link. What will be the RMS component of fundamental component of output phase with modulation index M? So it is, we know that it is nothing but M VDC by 2, and that is the peak value, that when you do divide by root 2, so that will be the RMS value. So that is what we have get answer, which is D. Then comes the question number 10. In question number 10, let us take the question number 10 quickly. So in question number 10, the PFC with flyback DCC converter, what we have is D of t is nothing but 1 by VSP sine omega t by my n V naught. VSP from the question at the peak, we will get when we keep omega t equal to 90, we will get Vs peak by n V naught, and that we will get 240 into root 2 divided by 400, that will be 0.702, and in the answer we have given. So in the answer it is given 0.6 to 0.7. That again we will increase the range of this one 0.67 to 0.72. So that's when we will be that will be the correct answer. So we will change this range and reevaluate that question as well. Okay, so this is all about this assignment number 5. That is the thing. Now let us see some of the questions which was asked during the yeah, we will change the range. So two questions will change the range. And in assignment there was a wrong option question. Wrong option means uh, the question has the option has to be changed, the that one. So that for that question we will be ignoring that question in the question number in assignment number 3. I think question number 4 kind of thing that will ignore, but this one we will change the range, and that's when you can the correct answer will be accommodated. Okay. Now there were some questions by the students, so which I thought uh, which cannot be answered through email. So we will try to answer that here. Now in the first question, it is given that the bandwidth should be in the range of Fs and Fsw. So what I mean by that? What I mean by that is, it means the controller shall not pass the circuit. Okay, so it's a cutoff frequency. Okay, now let us see if you wanted to, if you see in the, let me take the fresh sheet. Now, if you see, when you have to design any controller, any PI controller, any kind of controller, so what you have to see is we have a dual loop structure. Our current loop is the inner loop. Current loop is the inner loop. So since our current loop is the inner loop, the current feedback what we are getting, we have multiplied, I mean the current reference what we are getting, the output of the PI control of the voltage loop will get multiplied by the unit sine omega t or modulus sine omega t, depending upon what kind of converter is there. Whatever be the case, we were having a frequency variation of either 50 hertz or 100 hertz. Let's say if you are doing for boost PFC, it will be 100 hertz. So, and we wanted to track that 100 hertz component. So, what we wanted to track this 100 hertz component. At the same time, we wanted to reject that high frequency component, because in the current you also have a high frequency current which will be coming in, because you are doing the average current control. So now what you want a controller should provide high gain at 100 hertz, and should avoid or should attenuate the switching frequency component, FSW component. That is what you will get, because you wanted to just track the 100 hertz. Now since you have to track the 100 hertz from the our discussion Cp by 1 plus Cp, in order where C is the gain provided by the controller and P is the gain provided by the plant at that particular frequency. So what we have to do is we have to ensure that at that particular frequency, let's say if you wanted to have 100 hertz, you wanted to track down the 100 hertz, so you want that your controller must have a high gain at 100 hertz at that particular frequency of your concern. So now if you provide a very high gain, what will happen, this will go to Cp by Cp, and that will nothing but 1, which is nothing but your output by input, and that is when you can output by reference, and that is what you can do, that is what, because your reference has 100 hertz, so that is what you can ensure that your output is nothing but equal to reference, and since reference at 100 hertz, so your output will also be following that 100 hertz component. So that is why if you see your controller gain should have a very high gain at 100 hertz, and for 100 hertz, or you can say Fs, if line frequency is Fs, more precisely we can say Fs, and if you say our switching frequency Fsw, so I must provide a attenuation, that means I must provide a negative gain at Fsw, so that will be somewhere like this will be there. So that is the reason why the bandwidth has to be kept somewhere between Fs and Fsw. And since we do not wanted to provide any kind of we wanted to ensure that we are not providing any kind of gain from the closed loop control to the switching frequency component. So what we will do, we will keep this point. If we can keep this point Fsw by 10, we are very well off ensuring that these two conditions get satisfied. So that is what is all about the concept of providing a high gain to the to at that frequency for which you wanted the output should track down, which is there in the input. So that is what is all about this question which was asked by Milind. Then there was another question from Devashish. I would like to know how the designer decides the topology for PFC, meaning to say why is boost or flyback converter connected between the diode bridge and the load to perform PFC action. Why can other topologies like buck or buck boost or other isolated and non-isolated DC converter topologies not serve the purpose? See, the flyback is nothing but a what you can say derivative of buck boost. So buck boost can also be used there, but the problem with buck boost is you will get a negative voltage at the output. So you have to either use the derivative of buck boost, or you can use the flyback and give the reverse the dot polarity, and that's when you can get the the same the positive polarity voltage at the output. That is the first problem with the buck boost. Now here if you see, in all our PFC converter, what we are trying to do, we are trying to control the current which is going through the inductor, and that's when we can able to ensure that we have the unity power factor drawn from the source, and that's why we are getting the power factor got corrected. However, in case of buck converter, if you see, there is no inductor which is kept at the input. In buck converter, the inductor is kept at the output. So there is no way with which you can be in a position to control the average current which is flowing through the inductor. However, in case of flyback, you still have the control, because in DTS period you can control the amount. I mean, you can control the how much time it should be conducted so that the peak value goes in, and that time period you can vary, and that's when you can vary the the current is going through the inductor. But in buck converter case, we cannot do that because we do not have any inductor at the input. We cannot basically smoothen, or you can say you can provide any control to the current, to the input current, or you can say the current which has been drawn from the modulus Vs, which is indirectly nothing but from the AC source. So that's the this Devasi Chakravarti answer. Again, it all depends upon let's say you wanted to use obviously you are using mostly boost PFC operation. Why you are boost PFC converter? Why you are using boost PFC converter? Just because you have an input inductor, it is very easy to implement the average current mode control into that. And then you can have various what you can say derivative of converter. That is what I have given the question. One of the derivative of the boost converter I have given, buck boost, you can have, but again you have a negative voltage at the output, so that you have to keep in mind. Now the third question which was asked by Bhanu, which says that, sir, is there any significance behind q axis always leading the d axis, and if so, why? Okay, so now if you see, in our case what we have done, we have defined our alpha beta component, which is the alpha beta axis, which is the nothing but a stationary frame which are 90 degree apart from each other. That's when any vector or any space vector which is there, we can represent just by alpha component and beta component. We can represent the entire information about that particular space vector, Vs alpha and Vs beta, and then you can take the angles tan inverse Vs beta by Vs alpha. That will give you at what angle it is there from the alpha axis. Then you can take the magnitude under root Vs alpha square plus Vs beta square, and that is what you will get the your your magnitude of the vector, and once you know the magnitude and once you know the angle, you can represent that particular vector. So we just want a 90-degree phase shift or 90-degree phase displaced two axes, because why 90-degree? They are independent of each other, and we always wanted to represent. We always wanted to have a representative axis using which any vector in that plane can be represented, and that is why we have defined 90-degree displaced vectors. Now the next set of vector we have defined dq vector, which is actually rotating in the space, this rotating in the space using with the frequency same as that, the same as that of the vs phase space vector, which is rotating at omega speed. Now if you look very carefully here, the 90 degrees to be there, you can also take that q axis here. There is nothing like you cannot take, but once you define the q component in the lagging form, then you have to represent entire representation of going from alpha to beta, an entire circuit model will change accordingly. The reason why we take the q leading to that of d, yeah, we will provide that, will provide. Uh, the reason why we gave the q with respect to q leading the d is because we have already assumed that our space vector is rotating in the in the anti-clockwise manner, and that's why for our easy understanding we have defined the q in this way. But there is no hard and fast rule, it is just the mathematical substitutions, mathematical representation. You can give it in the other side as well. So that is what that answer to that particular query. Then comes your fourth thing, which is million. While calculating the average current, why we are calculating only the D ratio for S1 switch, as there will be current through the body diode just like the the IG bit. Yeah, million. Please.
Yes, I just missed one thing. I was actually asking for the MOSFET current. Like we have calculated only when the current is going from collector to emitter,
Hmm.
but we have not considered the values when the current is flowing from its body diode for the RMS value. So that was my question.
Mhm. So let me take down. I think it is in lecture number 26. Yes.
Yes, lecture 25.
25? No, I think it is 20, 27.
No, sir. No, sir. It's before 26.
It's before 26. So can you tell which lecture it is?
Yeah.
Okay, you tell me which lecture. By that time, I will come back again and discuss this problem. Then the
Okay, sir.
okay, fifth problem. I think fifth problem I have defined why this is the case. I have defined in detail while discussing the solution for that assignment problem. The same thing I have already discussed in there. Okay, this question I have already derived in the in the assignment, like why the option B is there. It is not same as PFC. It is not same as the flyback converter. That is what I wanted to say. This is a question where they say that okay. So the first thing is that they are asking question that why can't we directly write things in the dq axis, rather than first we are going towards the alpha beta and then we are going to the dq axis. So any three phase quantity, how we are going to dq axis, we are first represented that alpha beta into, first we are represented that three phase quantity into the three phase, into the two phase alpha beta, and then we are going into the dq. So similarly, our model, our circuit is actually being excited from the three phase system. So that is the reason why we have first, first we go from the three-phase system to the uh, two-phase system. That I mean, because in the circuit we can only write for the three-phase quantity. So that is the reason why we first go to alpha beta axis and then goes to uh, dq axis. Because if you see here, if you take only this part, just the directly the dq part, then we will not be able to see the impact of the phi component. This, because the phi is also changing with time. If you see our phasor, the angle between dq, I mean the angle between the d and alpha axis keep on changing with time. So that means the angle is also changing with time. So we have to also incorporate that angle when we are writing d by dt. So for that purpose, this we have defined in first. We go into the alpha beta and then we go into the dq. Here there is no place where that angle information is coming into picture. But when we define in alpha beta and then goes to dq, there we define, there we will have the angle component. And why particularly we are going, because any three phase quantity we are first representing in terms of alpha beta, and then from alpha beta we are defining the dq, this thing. So similarly our circuit model also will first define is alpha beta, which is a stationary frame, and then going to dq rotating frame. That's a question 6A that was asked by Anish. In question 6B, okay, since we are writing this one, why don't we write the voltage drop? No, we cannot write voltage drop omega L, because the moment we write omega L, we are not defining in terms of time domain. We have already gone into the frequency domain, and this expression L di by dt plus Rs, we are defining it in the time domain, because we wanted to capture that impact of that, how the angle changes with time. That particular information we wanted to capture. That's why we wrote our expression in terms of time domain, and then moved from a three phase model, I mean the equivalent three phase model, into the alpha beta model, and then from alpha beta model to the dq model. That's the thing. Yeah. Yeah.
Hello.
Yes.
Sir, in that the angle which we are explaining just now, what angle we are talking about that cannot come, like the theta
Okay.
angle, phi angle.
Okay, I'll show you. See, our if we see our representation, let me see, I think it's lecture number 27. Yeah, see this theta angle, this theta angle is also changing with time, and we wanted to capture that information as well.
Okay. Yeah.
If we just write the dq, we will not be having this theta angle information. And see, that is what is happening. This vector which is with there are two things which is happening. One is, obviously we are changing the magnitude of the vector to have the control of the current which is going through the inductor. At the same time, we are also controlling the angle of that vector. So we wanted, so you have to take down that angle as well as the theta information, I mean angle as well as magnitude information. So that is why if you write in terms of alpha beta and then goes to dq, you will have that angle information intact with you. Am I, you know
Yes, sir. Yes. Yes.
yeah. In lecture number 24, let me open the lecture number 24. Does my screen visible?
Yes.
Yeah. See, Milind, you hear what I'm trying to write here. If you see in this one, see this particular part, I'm writing for the MOSFET only. If I would have written for IGBT, that would have been a completely different expression. Since I'm writing for MOSFET and this duty ratio has that variation, that sinusoidal variation, so automatically this information is been taken, and we assume that whenever the current is going from, assume for MOSFET, oh, I cannot write here in this one. So for MOSFET, let me define the other one where I can write. Oh, system is getting them. Just wait. This one. So in this one, if you see when MOSFET is on, we know that when MOSFET is on, in the MOSFET what we have, in the MOSFET what we have is, we have a device and the diode. Now this diode comes into picture because of the construction of the MOSFET. And if you see, if you see the construction of MOSFET, any power MOSFET, if you see, this is your drain, this is your uh, n type drift region, then here you have the p well, and then what you have is, you have this n well, and this is nothing but your emitter terminal, and this is nothing but your drain, sorry, not emitters but source terminal, and this is your drain terminal, and your gate will be looking like this, obviously with gate G. So when you apply a positive potential between gate and source, what happens is that this P type which is there, P well which is there, this is N which is there. So what happens is that this, whenever you apply the positive potential, you will have a lot of electrons which get comes over here, and that is when this PN junction gets break down, and then you will form the channel. Now once the channel is formed, your current can go in this direction as well as in this direction. Both the direction it can flow. And if in the reverse direction, if the voltage across source to drain is smaller than the body diode, because this will correspond to the body diode, this this P and N junction will correspond to the body diode. So the this the moment you have this sorry, I saw it in the wrong manner. So the moment you have the voltage across the diode or across the MOSFET, I mean RDS on of this one going, if the current is going in this direction, RDS of the channel which has been formed multiplied by the current which is going is less than this uh, body diode, or you can say is greater than the cutoff voltage of this uh, or is less than the cutoff voltage of this diode, then diode will not turn on. And at the same time, when let's say the current is going through this MOS, through the diode, if I create the channel, it will flow through the channel, the current will flow through the channel, and the I is RDS on times I naught which is going, I value which is going, is less than my V forward voltage of this diode. So that is the reason why generally whenever the current, whenever the reverse current is flowing, that means from the source to drain, for the MOSFET they will create a channel, and that's when the current will start flowing through the channel. That is what generally people do, so that your conduction loss in the device can be reduced. So that is what we have taken over here. That particular scenario we have taken over here. So the moment we define duty ratio in that way, that means already we have already defined that the current will flow through the channel on whenever, I mean, whatever be the direction, whenever the with duty ratio this device is turning on, this channel is getting formed, and that much amount of losses will come through it. So that is what we have taken. Am I clear, Milen? Milen?
Yes, got your point.
Yeah, any other further questions? Sir, will the average value of I converter over the line cycle be equal to, let me, will be equal to the value that we find of the current found from the power balance? That is like a I converter over the line cycle.
Sir, is the question clear or should I
Yeah, yeah, you can ask the question. I mean, that is what.
Sir, what I wanted to ask is we have find the value of I converter from the power balance equation also. I'm talking about the lecture 25 we are
Yeah,
discussing.
yeah, okay, okay.
And then we have also find the whole equation of I converter, and then we have found what will be the average value in TS cycle, and means in the one switching cycle, and then in the whole line cycle. So will the average value, because when we are finding the RMS value of IC, means the current going into the capacitor, we told that okay, this is my I converter total, and then we are separating the average value of the I converter, which will be going into the load. So will the value, these two values, one which we find from the power balance equation and one which we are saying that this is the average value of I converter, will the both be having same value, or
Yeah, so
will
okay,
it have
so
some difference?
see there the reason why I have mentioned that particular average value is just to show that what will be the how the average value will vary if we do not have any other information. But yes, you can calculate that average value which is going minus, I mean, the same way you can do. So average value you can say it is the same as what we are getting. Average value is going into the load while the ripple part will be going through the capacitor. Yes, so they are mostly equal.
Yes, that's what I wanted to know. Means like that average value will be equal to that value which we will be finding from the power balance equation.
Yeah, yeah, that is.
Because in one of the question of the assignment, I was trying to do the same calculation. There was some difference around 1 to 2, around 1 ampere difference was there. So just wanted to confirm, because 1 ampere might be difference can is possible. Though I wanted to ask, will it be equal in any other calculations if
Yeah,
I?
you can share me that calculation, then maybe I can give you more better comparison. Maybe.
I will share on the email, sir. I
Ah,
don't have
sure,
at the. I will share.
sure, sure.
Thank you, sir.
Yeah, yeah. And any other further questions you have? Okay, let me also quickly discuss. I think we are already more than 12, but again, let me quickly discuss the very briefly how we can see how we can solve, what you can say, uh, the assignment 6. So if you see in assignment 6, see there are a lot of multiple choice questions are there. The main questions which which are there are actually your this part, question number 5, your question number 2, and question number 8. So you can use this concept to solve this part. It's a simplistic thing for assignment 6 hence. I'll say. The cross coupling term, in order to avoid the cross coupling term, it is simply for q axis, it is nothing but your omega L IST by G. And this G you can calculate using the information given. This G is nothing but the amount of gain you will get, the ratio between the your your control voltage by the actual output voltage which you are getting, that you can see from the lecture. Now here ISD you have to calculate, so what you can do, simple, you can calculate the ISP and then multiply it by 3 by 2, so that will be your ISD. Because when the DQ axis is lying along the alpha component, that is when you can get your value, which is nothing but ISP times 3 by 2 value. So that you can take, and you can, using that you can, I think all the other informations are being given, you can easily calculate that particular part. Then in the question where you have to calculate the for controller, current controller, the Kp and Ki, I'll simply, from the equation you can just take Kpc by L by G K1 T sigma. All the informations are been given, so you can directly use this thing and to obtain that. And then you can calculate KIC, which is nothing but Kpc by Ts, which is Ts is nothing but L by R. You can easily calculate, or I mean L by Rs. L we know, I mean L value, you can either calculate, from the question, and then RS value, RS value will also be given. If I look at the question, I think all the informations are being given. L value, RS value. I think it is straightforward question. You can just put it and you will see that one. Now this one is also quite a straightforward question. You can see this one is again same for problem. You can take that. Now in this question, the third question, if the D and Q axis is being given, so you can just do a simple, it is simple mathematics kind of thing. You can just look around. See, what we have is, we have the D component and we have the Q component, and we have the beta component and we have the alpha component. And what we are trying to do, we are trying to aligning our Vs phasor along the D axis, and we are also trying to assume, I mean in our operation we wanted the Is phasor also to be along this, by how we can make sure, by making the Q component to be 0. For power factor can use, okay, so that is what I'm trying to say, no. So let's say if your Is phase is, let's say you are, in general case, here we are assumed that it is a straightforward, unity power factor. That means my Is phasor is also along this one. What it indicates? It indicates that my ISD value is some non-zero value and ISQ value is a 0 value. So what is my angle between them? Angle between them, Vs phasor and Is phasor, is equals to 0, and that you will get is nothing but tan inverse 0 by ISD, which is nothing but equal to 0. That is what we will get. Now assume you are you have a case where your Is phasor is somewhere around, let's say not unity, somewhere around here. What it indicate when the Is space vector is here? What it indicate? It indicates that when we take the component along the D axis, some ISD is there, and when we take the component on Q axis, some ISQ is there. That means if we see in this triangle, what it indicates, we have this ISD, we have this ISQ, and finally this is your nothing but your resultant phasor. This is the resultant phasor resultant vector Is space vector. Now you just calculate this angle, angle phi, which is nothing but will give you the angle between Vs space vector and Is space vector. That means you will have the same kind of phase in the phase voltage between, in the phase voltage and phase current, and from there you can easily calculate your power factor angle. So I think I have given you enormous hint using which you can easily solve this problem. Okay, I think Monica, for power factor we can use, yeah, that is what I have told. You have to calculate in that triangle what is the angle, and that is what is simple, cos of that angle will be nothing but your power factor. Yeah, so that's it. If you have further questions, you can ask. Otherwise, we can end this call. So this week, coming week, you will have lectures from isolated DCC converter. Then after that week, we will discuss in detail about phase shift full bridge converter and its operation. And after that, we will see some things on the DAB and some on the magnetics. And after that, we will start our uh, different charging procedures, like when you plug in the charger into the vehicle, what are different charging sequences are there, what are different charging processes are there, how vehicle recognizes that charger has been plugged in, how charger recognizes that vehicle has been plugged in, different kind of terminologies and different status we will see after, I think from 40, lecture number 48 we will start that, and it goes up to lecture number 60. Yeah, any further questions you have, we'll ask, otherwise we'll end for today's live session. Okay, so that's it. Thank you. We'll meet in the next weekend, on the next weekend, discussing some of the problems and going ahead and discussing solutions. Thank you. So we also had last week also we had a session. Please go through the live session. If you did not able to attend that, please try to attend. I think I'll keep the time maybe this time only, because in this time I can see a lot of people are joining. So maybe I'll keep this time. Generally at this time, we keep. I mean, I keep from 3 to 4, because that is a time when I feel most of the generally on weekends people would like to start their day quite late. So that is the thing. But no ways, I will start the session from the next time. Maybe the same time slot will keep 11 to 12, and that is how we can go ahead. Yeah. So every week we will meet. So that's when you can your doubts and queries can be answered. You know immediately, and we're trying to answer your queries from the mails. If some of the queries are very difficult to answer through mail, so that's why we are taken them those queries during the live sessions. Yeah, thank you for that. Maybe that will help for the timings. Yeah, actually we can have, but there are many students are there. It is really difficult for I mean, to converge to a single point. I understand. See, last time I have kept 3 to 4, three. See, first session we did it on weekdays. I avoided weekdays because I realizes a lot of people are from industry also. They cannot join on weekends. So, and also you also have. I mean, students are also there. They also have uh, classes going on. So that's why I shift to weekend. So weekend I thought, okay, 3 to 4 is a good time, but again I realizes 3 to 4. I mean, only 1 or 2 people join. So that's why I have now shift to 11 to 11:30. I think this is a fairly good time. I think good amount of people are there, and let's say if you are not able to attend this thing, you can able to join through the you can see the live sessions, and again if you have further questions, you can obviously write to us. We are there to answer it. Yeah, I hope you are liking the course and are going nicely. Everything is going nicely. Yeah. Thank you. So we will end this call.